Hello students, welcome to Shri classes. We'll continue with the lecture number 5, magnetic effects of electric current. In this section, we'll be studying electromagnetic induction, Fleming's right hand rule and electric generator. Even though this electric generator is taken out of your syllabus, from the future point of view, from the future studies point of view, we'll rush through the working, the principal construction and working of electric generators, in which we are going to see AC generator and DC generator. So let us start with the electromagnetic induction. Michael Faraday, he was the first person to inform that, to discover that a moving magnet can create an electric current. How nice it is to hear, but he was the first person to say that a moving magnet can create an electric current. EMF means electromotive force, which is the potential difference. So he was the first person to say that a moving magnet will create an EMF and hence a current. So let us see a little bit brief history about Michael Faraday. I'll read it for you. Michael Faraday was an experimental physicist. He had no formal education. He worked in a bookbinding shop during his early years. He used to read books that came for binding. This way, Faraday developed his interest in science. He got an opportunity to listen to some public lectures by Humphrey Davy of Royal Institute. He made careful notes of Davy's lectures and sent them to Davy. Soon, he was made an assistant in Davy's laboratory at the Royal Institute. Faraday made several path-breaking discoveries that include electromagnetic induction, which we are going to study, and the laws of electrolysis. Several universities conferred on him the honorary degrees, but he turned down such honors. Faraday loved his science work more than any honor. So Michael Faraday was the first person to talk about or discover electromagnetic induction, which we are going to study. So he said in 1831 Faraday made an important breakthrough by discovering how a moving magnet can be used to generate electric currents. In order to understand electromagnetic induction, we need to understand what is magnetic flux. Magnetic flux is the number of field lines passing through a certain area. Suppose this is an area over here and these are the field lines. So the number of field lines that pass through a particular given area is called magnetic flux. This definition of magnetic flux is required to understand the electromagnetic induction, where we use the keyword magnetic flux. In this formula, of course the formula is not there for you. Magnetic flux is given by B into A into cos theta, BA cos theta, where B is the magnetic field strength and A is the cross section area, and cos theta, of course, angle between the magnetic flux and area vector. Area vector and all, leave it for your standard, not required. So far we have been studying area as a scalar quantity, but area also can be a vector quantity, which you will be studying in PUC2. It is called the area vector. So angle between the magnetic flux and area vector is called cos theta. I am not interested in cos theta. Let us understand magnetic flux is nothing but let the angle between the area vector and the magnetic field lines be 0. Cos 0 is 1, and therefore I can consider phi equals B into A. Not required. All these things are not required. B is magnetic flux field strength in Webers, and area is in magnetic field strength in Webers per meter, and area is in meters. So meters cancels. Finally, the unit of measurement of magnetic flux is Webers. Okay, anyway, that is not required. What is magnetic flux? Number of field lines passing through a particular cross-section area is called the magnetic flux. How to define electromagnetic induction? Whenever there is a change in magnetic flux linked to the coil, an EMF and hence a current is induced into the coil. and this phenomenon is known as electromagnetic induction. ये definition आपको रट देना पड़ेगा, या फिर you have to understand, या फिर रटना पड़ेगा. That is very important. How is the textbook definition? The process by which changing magnetic field in a conductor induces a current in a conductor, and this is called electromagnetic induction. This definition is simple, no? The process by which a changing magnetic field induces a changing magnetic field in a conductor induces a current in another conductor. A changing magnetic field in one conductor induces a current in another conductor, and that is how this process or the phenomenon is called electromagnetic induction. Now it is very difficult. Once if we go through in detail with the diagrams and all, probably the definitions can remain in our brain. It should remain there. So whenever there is a change in magnetic flux linked to the coil, an EMF, and hence the current is induced into the coil, this phenomenon is known as electromagnetic induction. EMF is called electromotive force. Electromotive force is nothing but the potential difference or the voltage. So, and what else? Faraday's laws of electromagnetic induction. There are two Faraday's laws. Even though these are not there, in honor of Mr. Faraday, at least we should know what are the Faraday's laws of electromagnetic induction. Of course, these have been introduced in your plus 2, but I hope these two laws at least would have been introduced in your 10th standard formally by introducing his name and the laws also in your textbook. That is not done, but let us study. Whenever there is a change in magnetic flux linked with the coil, an EMF, and hence the current is induced into the coil. This is the first law. And second law talks about the magnitude of the induced current. So the magnitude of the EMF and hence the induced current is directly proportional to the rate of change of magnetic flux linked to the coil. It is better to understand with the diagrams this phenomenon. One more small part here. What is a galvanometer? Already this I think we discussed in, I don't know whether we discussed in current electricity or not, but what is a galvanometer? It is an instrument which can detect the presence of small amounts of current. So that is the galvanometer, and that is used in this experiment. So first experiment here, this is a solenoid. It looks like a solenoid. An insulated copper wire is wound on a non-conducting pipe here. This can be a PVC pipe, something like that. PVC pipe, which should be a non-conducting pipe. An insulated copper wire is wrapped around a non-conducting pipe here, and the ends of the coils are connected to the galvanometer. In the galvanometer, as you see here, the pointer is at 0, which is at the middle, and there are some readings over here and there are some readings over here, and the galvanometer can point either toward this side or towards this side based on the direction of the current. You got it? Based on the direction of the current. If the direction of the current is from left to right, it may bend on one side. If it is right to left, it may bend on the opposite side. Okay, that's how the galvanometer. That means normally the needle is at the center, but based on the direction, it may deflect either this side or that side. If there is no current, zero current, the pointer is at the middle, which is 0 here. I hope this is clear for you. Next. So here the galvanometer is connected to the ends of the coil, and there is a magnet. What is that Mr. Michael Faraday said? Michael Faraday said a moving magnet can create an electric current. Yes, of course. Here, whenever this magnet is moved inside, this galvanometer shows some deflection on one side. Retrieve back the magnet. The galvanometer shows the deflection on the opposite side. Meaning, whenever this magnet is moved inside like this, the galvanometer deflection, the galvanometer needle shows the deflections like this. What is the indication here? The moment the magnet is moved, the galvanometer shows the presence of current, meaning movement of the magnet is causing the production of potential difference into the coil and hence the current. So what we say is the movement of the magnet causes an induced EMF and thereby induced current. It causes the potential difference is induced into the coil, and it also induces the current into the coil, and the presence of the current is detected by the galvanometer. Now, according to Faraday, what it says is the statement electromagnetic induction is, I think let me explain this on the board. It is preferable because here magnetic flux lines are not shown, and therefore we'll study on the board what is that it causes over here. How this current and the voltage is induced into the coil, we'll study with on the board here. Magnetic flux, number of field lines passing through a particular area, represented by phi equals B into A. Here this is a solenoid or a coil, you can say. The two ends of the coils are connected to a galvanometer. This coil is an insulated copper wire wound on the non-conductive PVC pipe, you can say. It is a non-conductive material. It can be a plastic pipe or a PVC pipe, cylindrical pipe, on which this insulated copper wire has been wound. This is a magnet. The field lines are from north to south. One line I have shown here. Of course, these are all continuous curves basically, but to understand, only few magnetic field lines have been drawn here. Now, according to Michael Faraday, what is that electromagnetic induction? It is a phenomenon in which whenever there is a change in magnetic flux linked to the coil, then an EMF and hence the current is induced into the coil. Meaning, whenever there is a change in magnetic field lines associated with this coil, if I move this magnet like this, the magnetic field lines associated with this coil change. Meaning, in the beginning, only few lines will cut across this coil, but as and when I move over here, more and more number of lines would be cutting across this coil. That means there is a change in magnetic flux linked to the coil. That means number of field lines passing per unit area of this cross section of this coil is gradually increasing, and therefore there is an EMF. Therefore there is a change in the magnetic flux linked to the coil, and hence an EMF is induced into the coil and hence the current. So whenever there is a change in magnetic flux linked to the coil or associated with the coil, then an EMF and hence the current is induced. So you insert this magnet inside. As long as the magnet moves continuously, the galvanometer shows the deflection on one side. Stop inside, the motion of the magnet, the movement of the magnet stop inside, the needle comes back to 0. Now retrieve the magnet backwards. Once again, continuously retrieve the magnet backwards. The needle of the galvanometer deflects on the opposite direction. Say for example, this is the needle here. If I am moving this magnet inside here, this will show towards this deflection. The moment I stop the magnet, it comes to 0. The moment I start retrieving backwards, the galvanometer needle deflects this way. When I stop this, it will come back to 0. I hope you are able to understand. So when the magnet is moved inside, the galvanometer deflection could be on one side. When the magnet is retrieved in the other direction, retrieved backwards, the needle deflection is on the opposite side, indicating that the direction of the current is reversing. It is getting reversed when the motion of the magnet, when the movement of the magnet is reversed. So this is all about electromagnetic induction. So once again here, whenever this magnet is moved inside, the magnetic field lines associated with this coil change, and hence an EMF and the current is induced into the coil, the presence of which can be detected by the galvanometer. When the magnet is moved inside, the needle of the galvanometer moves on one side. When the magnet is retrieved backwards, then the needle of the galvanometer shows moves in the opposite direction, indicating the direction of the current is reversed. But remember this observation, the deflection of the needle of the galvanometer is observed only and only when the magnet is under motion. Meaning continuously whenever the magnetic flux linked to the coil changes, only during that time you can observe the induced current. The moment the magnet becomes stationary, no more change in the flux associated with the coil is observed, and hence the EMF becomes 0, current becomes 0. So only under the motion of the magnet continuously, the magnetic flux linked with the coil changes and EMF is induced, and hence the current is also induced. I think this is what I hope you must have understood very clearly. The same experiment can be done by using two coils. Let us have a look at the PPT first, and then once again I'll talk about that. Or can we complete a couple of points are there? Let me check here about the magnitude of the EMF. Also will check here itself. I am reading certain points from my PPT with respect to this diagram. An EMF and current can be induced in a coil either by moving the coil into a magnetic field or by moving a magnet into it. You can either move the coil like this, keeping the magnet stationary, or the magnet can be moved like this, keeping the coil stationary. Both will result in the induced EMF and hence the current. The induced EMF and hence current is due to changing magnetic field lines associated with the coil. That means the number of magnetic field lines, which is called the flux. The induced EMF and hence the current is due to the changing magnetic flux or changing magnetic field lines associated with the coil. Factors on which the induced current depends upon. Let us see the magnitude of the current over here depends on which factors. First point, induced current can be increased by rapid motion of the magnet or the coil. That means if I move this magnet rapidly like this, the magnitude of the current is more and you can observe larger deflections. Make it slow movement, only slight deflection. Rapid motion, larger deflections, indicating magnitude of the current is more. So it is nothing but the speed of motion, the speed of movement of the magnet basically we are talking about. Or indirectly I can say it is phi divided by T. What is phi? Magnetic flux divided by T, meaning the magnitude of the induced current depends upon the rate of change of magnetic flux associated with the coil. Okay, that's one thing. And second point, by using the strong magnet, by increasing the magnetic field strength of this magnet, we can increase the magnitude of the induced current. Next, by increasing the number of turns in the coil and the area of cross section of the coil. Here this can be made a little bit more bigger coil, or also by increasing the number of turns per unit length in this case. Or you can also say, see, you must understand very clearly the difference between a solenoid and a coil. Solenoid is, large number of coils, large number of or a copper wire, insulated copper wire wound in the form of a cylindrical shape, and coil refers to basically all those rings are joined together to form a coil, something like this. Whenever I say a coil, you must also understand that this is a coil basically. This is how the coil it refers to. Yeah, this is a coil. It can have more number of turns or it can have one only. So more the number of turns, the magnitude of the induced EMF can be increased. See, instead of taking a solenoid, I can take one coil consisting of n number of turns and try to move the magnet inside. Yes, and move inside. When you connect it to the galvanometer, here also the pointer deflects, indicating that the movement of the magnet, because of the movement of the magnet, the magnetic flux linked with the coil changes, and hence an EMF and current is induced, which can be detected by the galvanometer over here. Okay, so thing is, third one, by increasing the number of turns of the coil and the area of cross section of the coil, make a little bit more area, then also the magnitude of the current can be increased. Note, the induced current is found to be highest when the direction of motion of the coil is at right angles to the magnetic field. Suppose if I am moving a coil over here and this is a magnetic field and the area of this cross section area of this coil should be perpendicular to each other. In that case, you can find the magnitude of the induced current is maximum. Meaning, I can keep this magnet also tilted way. This way also I can tilt, or this way also I can tilt, but you can find the maximum EMF if I tilt this, if I move this magnet perpendicular to the cross section area. Therefore, these are the factors. So once again, what are the factors? Induced EMF or the current, induced current, magnitude of the induced current depends upon the motion of the magnet. Rapid motion increases the induced current. By increasing the strength of the magnet, current induced can be increased. By increasing the number of turns per unit length, or by increasing the number of turns in the coil, induced current can be increased. So this is about the electromagnetic induction by movement of magnet. Now the same experiment will try to carry out a little different way, and there let us see how electromagnetic induction is observed. So let me go to the PPT now and then let's see. For making notes, electromagnetic induction, definition of the flux, Faraday's law. Whenever there is a change in magnetic flux linked to the coil, an EMF and hence the current is induced, and magnitude of the induced EMF depends upon, it is directly proportional to the rate of change of magnetic flux linked to the coil. So these are the two laws. Note on this. Galvanometer, a small note you can make. This also electromagnetic induction, all these points I have discussed. Pause the video to make a note. Now this is a small experiment here. Here also we observe the electromagnetic induction. Let us see here. There are two coils. This is this coil. See here, what is the experimental setup is, an insulated copper wire is wound on an insulated pipe here. What they say, non-conducting cylindrical roll. This coil, insulated copper wire, is wound on a non-conducting cylindrical roll. It can be a PVC pipe also. One coil contains more number of turns, say 100, and another coil contains less number of turns, and say about 50. The one that contains more number of turns generally we call primary coil, and the one which contains lesser here can be termed as a secondary coil. First primary coil is connected to a battery with a switch, and secondary coil is connected to the galvanometer. Here what is peculiar thing observed here is, whenever we switch on and switch off, only during that moment, a momentary deflection of the needle of the galvanometer is observed in this here. Meaning, whenever this switch is on and off, during that moment, an EMF and hence current is induced into this coil, which is detected by the galvanometer. How it is possible here? The moment I switch on this coil, a current passes through this coil, and this coil becomes a magnet. It produces magnetic field lines, and those magnetic field lines are cut across by this coil. Therefore, the magnetic flux linked with this coil is said to change. As the magnetic flux linked with this coil change, an EMF and hence a current is induced into the secondary coil that is detected by the galvanometer over here. So this is an experimental setup, and see, this is an activity. Generally you will have a question, describe an activity to show that whenever a current is made to pass through a primary coil, an EMF is induced into the secondary coil and hence the current. So this activity needs to be described. Now a little bit I'll try to explain this on the board, and then you can get back to, I'll direct you to the PPT for making suitable notes. Here we will see, this is a primary coil, this is a primary coil, secondary coil here. The moment you switch on this coil behaves like a magnet, a bar magnet, and it produces magnetic field lines. So just to show you a couple of field lines, I can draw something like this. Something like this. Okay. Those are all not intersecting, okay? Important. Something like this. Field lines. So these field lines, whenever we switch on, the moment we switch on, the coil behaves like a magnet and it produces magnetic field lines. As this secondary coil is placed nearer to this one, but there is no actual contact between these two, as this is placed nearer here, the field lines associated with this coil increase because magnetic field lines are getting produced. The field lines associated with this secondary coil increase, or I can say the field lines associated with the secondary coil change, and hence a current is induced into the secondary coil, which is detected by the galvanometer. After a certain time, see, this change in the deflection is observed only momentarily. Why momentarily? Once this becomes a magnet, the field lines will get stabilized, meaning the number of field lines associated with the secondary coil will not change. It is fixed number of field lines that cross the secondary coil, and therefore if there is no change in the flux associated with the secondary coil, the galvanometer, there is no current induced, and the galvanometer shows the zero reading. There is no deflection. In the beginning, the moment the plug key is on, switched on, inserted, the plug key is inserted, suddenly the field lines increase and the number of field lines associated with the secondary coil change, and hence EMF is induced. The same case is observed during switching off. The moment we switch off, all these field lines will vanish, meaning instantaneously the field lines linked with the secondary coil will decrease the number of field lines, and therefore instantaneously, because of the change in magnetic flux with the secondary coil, an EMF is induced and the current is induced in the secondary coil. After some time, this does not act like a magnet at all. There are no magnetic field lines associated with, there is no change in the magnetic field lines associated with the secondary, and there is no current. And therefore, you must remember, the flux linked with the secondary coil changes only during switching on and switching off operations, and hence instantaneous or momentary induced current is observed in the secondary coil, detected by the momentary deflections of the galvanometer, like this during switching on and switching off. I hope you are understanding this very well. Okay, this is another experiment, and here also, how do you increase the induced current over here? You can make this magnitude of the current, number of turns per unit length of this coil. These are the two ways by which, also by increasing the cross section area. That means, according to Michael Faraday's second law, the magnitude of the induced current is directly proportional to d phi by dt, or you can say I is proportional to, or of course voltage is also, you can say EMF is proportional to. It is better if I write EMF is proportional to, and therefore the induced current also, because voltage and current are directly proportional. So the PD is proportional to phi by t here. What is phi? The number of field lines per unit area, or through a certain cross section. Therefore, the rate of change of magnetic flux, if the rate of change of magnetic flux increases, the potential difference increases and the current induced also increases. I hope you have understood these two experiments very well. Now I will direct you to the PPT for making some notes. Here, this is an activity, you can read it, and the same description which has been given here, maybe some points you can note it down, pause the video and note it down. So let us proceed to the next now. direction of the induced EMF and hence the current is important. See, as I said in our I hope you should you must be remembering Fleming's left hand rule. What is that we used it for? A current carrying conductor when placed in a magnetic field experiences a force and the deflection. The force and the deflection direction can be identified by Fleming's left hand rule. Here Fleming's right hand thumb rule, this is a Fleming's right hand thumb rule. This right hand thumb rule is used to identify the direction of the induced current over here or the induced EMF. Okay. Here also what it states is we have to stretch the first three fingers of the right hand mutually perpendicular to each other. Once again, MFC doesn't change, motion, field, current. Here if we know the motion of the conductor, that means the coil, in case of the magnet and the coil, the motion of the coil can be considered, because either motion of the magnet or the coil, the movement of the coil into a magnetic field also induces the current in the coil. So M, motion of the conductor or the coil, F, field, this is the motion, the direction of the field. If these two are fixed, then the middle finger gives the direction of the induced current, and hence stretch the thumb, central finger and forefinger of your right hand mutually perpendicular to each other. If the forefinger points towards the direction of the field and the thumb indicates the direction of motion of the conductor, then the central finger gives the direction of the induced current. Okay, and this is used to find the direction of induced current in a conductor moving in a magnetic field. Remember, here this Fleming's right hand rule is used to find out the direction of the induced current whenever the coil is made to move in a magnetic field. That is important to know about this. So where do you use, what are the applications of this one? In generators, AC generators and DC generators, we need to identify the direction of the induced current, because we know the direction of the motion of the conductor there and the direction of the magnetic field. Whenever a coil is moved into a magnetic field, a current is induced into the coil, and that is called electromagnetic induction, isn't it? So that is used in generator, basically AC generator and DC generator. Let's see what else is there next. Yeah, direction of induced EMF. One interesting point over here, dear students, Fleming's right hand thumb rule, right hand rule, it is used to find out the direction of the induced current when the coil is moved into a magnetic field. But surprisingly, in this case, that is a solenoid type of assembly over here, or for that matter this can be a coil also. This is a solenoid here, it can be a coil also. You know already the difference between the solenoid and the coil. In this case, the direction of the induced current by applying Fleming's right hand rule is not possible. It is not possible in this case. It is very difficult to you to understand also. It is not even it is very difficult for everyone to understand also that. And therefore, as you can expect the question something like this, mark the direction of the current in the coil here if the magnet is moved inside the solenoid. In this case, how will you mark this? Upward or downward? The arrow of the current in this coil, whether it is upward or downward. It is very difficult to apply the Fleming's right hand rule and find out the direction of the current over here, and therefore we use something different called Lenz's law. Even though Lenz's law is not there, it is not there for you, the question appears to identify the direction of the induced current in a solenoid whenever the bar magnet is moved. Generally this question comes in the exam. To answer that, you must know the Lenz's law. So what is that it states about? According to Lenz's law, the direction of the induced EMF is such that it opposes the cause that produces the EMF. You understood? So here a small example is given here. We'll do it. We'll see here what happens. This north pole, when it is made to move inside the coil, according to Lenz scientist, this coil tries to oppose this motion of the magnet. Here it is a north pole. Here this is a north pole. If this coil has to oppose this magnet, it acts like a north pole, and two like poles will repel each other. And therefore, if the north pole is brought near the coil behaves like the north pole. If this behaves like a north pole, we know that in a coil, north pole is the one where the current flows in anticlockwise direction. And therefore, here if the magnet is brought near this, I can put the direction of the current over here as downward here. You understand? That means, shall I explain it on the board? It is better. Once if I explain, I think explaining on the board is better than the small diagram. I feel so. Let's go to the board. I list the clock rule here in order to understand the direction of the induced EMF into this solenoid. So let me use the clock rule. If this is a coil here, and if the direction of the current in the coil is anti-clockwise direction, then the coil behaves like a north pole. So the direction of the current in this is this way. It is anti-clockwise. If the direction of the current in the coil is anti-clockwise, then that phase behaves like a north pole. Similarly, if the current in the coil is clockwise, then that phase of the coil acts as a south pole. Yes, here. So based on the direction of the current in the coil, we can conclude whether it is a north pole or a south pole. Clockwise, south pole, and anti-clockwise direction, north pole. North pole. So now here this magnet is moved inside. Let us see what is the direction of the induced current in this coil. As this magnet comes towards this, according to Lenz's law, what is that it states? Lenz's law states that the direction of the induced current in the coil is such that it opposes the one which produces that induced current. That means the direction of the induced current in the coil is such that it has to oppose the motion of this magnet, because motion of the magnet or the movement of the magnet is causing an induced EMF or induced current. So the direction of the induced current is such that it opposes the movement of the magnet here. If this north is coming towards the coil, in order to oppose this force, oppose this movement of the magnet, the face of the coil must behave like a north pole only. North pole only. Because this is, whenever the current flows through this acts like a magnet, no? A current carrying conductor produces a magnetic field. So whenever this magnet is brought near this one, this face opposes the movement of this magnet. In order to oppose this face has to act like a north pole. If this face has to act like a north pole, then the direction of the current in this phase, if you look from here, it should be anti-clockwise. If it is to be anti-clockwise, you see from here the current has to be anti-clockwise. The current has to be anti-clockwise, and therefore the direction of the current is like this. I can mark this. This is whenever this is moved inside. You got it? That means, the moment you push this magnet inside, these are the field lines, okay, and similarly the coil also behaves like a magnet because of the induced current, and this also will try to oppose this. So in order to oppose this, the face of the coil becomes a north pole, and in the north pole we know that the direction of the current is anticlockwise. So if you see from this face, from this side, the face of this, the current is flowing this way, anticlockwise. Only when the current flows anticlockwise, this face becomes a north pole and would be able to oppose the movement, the incoming of the north pole. So how to remember this? If north pole is coming, the coil says stop, don't come. When it says don't come, when it acts like a north pole. If it has to act like a north pole, the current in this coil should be anticlockwise, and therefore I have marked like this. Now interestingly, what happens if this magnet is retrieved backwards? If this magnet is retrieved backwards, something like this, suppose the magnet is over here and this magnet is retrieved backwards. In that case, what is the polarity of this? In which direction the current flows in this coil? See here, if this is north pole of the magnet here, north pole, and this is the south pole. If the magnet is retrieved backwards, this north pole moves away from this, then the coil says come, please come. If this coil has to invite this north pole, the coil has, this face of the coil has to become a south pole, because unlike poles attract each other, and therefore the current in this coil moves in the clockwise direction. So if this magnet is moved backwards, then the direction of the current gets reversed. That will be, I am showing it by red here. If this magnet is moved backwards, the direction of the current is red color, that is clockwise direction. I hope you are able to understand. You must have listened very carefully. If you have listened carefully, you will be able to understand. So once again, according to Lenz's law, if this magnet is moved towards the coil will oppose this north pole. In order to oppose the movement of this north pole, the face of the coil has to act like a north pole. It can act like a north pole provided the current in the coil flows in anti-clockwise direction, and therefore I have marked this here. If you see from this side, this is anti-clockwise, and therefore the arrow is like this. Now when the magnet is retrieved backwards, the north pole is moving away, but the coil says you come, because it would like to accept that one, because it wants to produce the opposite effect. So if north pole is retrieved, then the face, in order to attract the north pole, it behaves like, the face of the coil behaves like a south pole. In that case, the direction of the current is clockwise according to the clock rule, and hence if you see from that side, the current flows in the clockwise direction. So this is how we should be able to mark the direction of the current, induced current, based on the movement of the magnet or based on the movement of the coil also. Okay. So what we have studied today is electromagnetic induction. I would like to summarize it before we go to the generator. See, all these lessons, in the first case we studied Oersted experiment, which is a current carrying conductor produces a magnetic field. Second one, we saw a current carrying conductor, when placed in a magnetic field, it experiences a force and a motion. Meaning, suppose if these are the poles over here, north and south, and if one coil is there, and for that if we connect electric current, if a current is passed through the coil which is placed in the magnetic field, then the coil rotates. Now Michael Faraday said, instead of connecting the battery to the coil where it rotates, what we do now is you rotate this coil in the magnetic field. This is how it is. Let us correct the galvanometer. Now what we will do is, this one with the handle, this rectangular coil, you rotate in the magnetic field, north south in the field. Mechanically you rotate the coil. There is an induced current into the coil which is detected by the galvanometer. So all these are linked. A current carrying conductor produces a magnetic field. A current carrying conductor when placed in a magnetic field experiences a force and therefore motion, that is the DC motor. And last case, a generator case, that means if we move a conductor in a magnetic field, a current is induced into the conductor according to Faraday's laws. Okay, so these are the three main important concepts, and based on the electromagnetic induction principle, you know, the generator works. So let us make a few notes of the PPT, and then we'll study the generator. There are two AC and DC generator. We'll try to finish off that very quickly as possible. Okay, yes, you can make a note of all this. Direction of the induced EMF and hence the current, important. Fleming's right hand rule is used to find the direction of the induced current in a conductor that moves in a magnetic field. So this is the right hand rule which we studied. And the direction of the induced EMF in a solenoid is given by the clock rule which I discussed. You can make a note of this one. And finally, we look for electric generator. What is a generator? It is a device which converts mechanical energy into electrical energy. For example, in all our apartments and all, the generator will be installed. What is that it does? You have to put a diesel in that, no? Then only it can give you electricity, electric current. Why we should put the fuel there, diesel? Because by putting the diesel, there is an engine which runs, and that engine rotates the coil inside the magnetic field. So whenever a coil is rotated mechanically inside a magnetic field, a current is generated into the coil, and that current is taken out. It is stepped up to a required voltage using the transformer, and then it is distributed across the apartments. Of course, the same principle holds true in the power generation stations also. So what is the electric generator? It converts mechanical energy into electrical energy. And what is the principle of generator? It works on the principle of electromagnetic induction. Whenever there is a change in magnetic flux linked with a coil, an EMF and hence a current is induced into the coil, and this phenomenon is called electromagnetic induction. What are the types of generators? There are two types, AC generator and DC generator. AC generator means the generator produces an alternating current where the direction of the current changes. Okay, the direction of the current changes. How many times? It depends upon the frequency, which we'll study later. And DC generator is the one in which the current direction in the external circuit is in only the same direction. Whereas alternate generator, the direction of the electric current in the alternate external circuit changes alternatively. In direct current DC generator, it remains same. So AC generator working principle, this is the construction. Working also I will explain here itself. See, AC generator consists of, similar to our motor, it consists of permanent magnets north and south. A, B, C, D is a rectangular coil. R1 and R2, this is R1 and R2, these are called slip rings or slip ring commutator, and B1 and B2 are the carbon brushes. And here there is a load here. You can put a galvanometer to detect the current generated into this coil, which is taken out externally, or it can be a tube light which glows, or it can be any resistor. If you keep a resistor, it will heat. It can be a heater, meaning instead of galvanometer, I can also have a load over here. Okay, so north south permanent magnets, A, B, C, D is a rectangular coil. R1, R2 are the slip rings. R1, R2 are the slip rings. B1, B2 are the carbon brushes which are pressed against the slip rings. These slip rings are copper bushes, hollow copper bushes, externally conductive surface and internally insulated, that is mounted on an axle once again. And B1, B2 are the carbon brushes which are pressed against these slip rings. Slip rings are also called R1, R2 slip ring commutators. And finally, both the brushes B1 and B2 are connected to a galvanometer to detect the direction of the current. Let us see how this cycle works. There are two diagrams given, beginning of the cycle and the next half cycle. In the beginning of the cycle, we have to move this current, we have to move this rectangular coil in the magnetic field. According to Faraday, if we move the conductor in a magnetic field, current is induced by electromagnetic induction. Here, let us try to move this conductor. That is, ABCD is a coil, rectangular coil. AB is the conductor, arm of this coil. Let us try to move this AB upwards here, out of this. That means, let me rotate this coil like this in the clockwise direction. If I rotate this in the clockwise direction, what is the direction of the induced current is what I am going to explain. So, arm AB moves upwards if this is rotated in a clockwise direction. This arm AB comes this way, arm CD goes downwards. So, in this case, how is the direction of the induced current? Let us apply Fleming's right hand rule. So, Fleming's right hand rule is used to identify the direction of the induced current. Here, arm AB moves up. So, thumb should indicate the motion of the conductor up. MFC, the index finger should direct it towards the field, that is like this. The index finger should point towards north to south. I can say like this. Yeah, exactly like this. So, index finger north to south. I don't know whether they are able to see it. Index finger, see here whether it is correct. Okay. Index finger north to south, and thumb indicates arm AB towards you. In that case, the middle finger indicates the direction. Can you see here along the arrow, my middle finger along the arrow? Therefore, the direction of the induced current here is my thumb here, which is along this arrow. That means the direction of the induced current is from A to B in this arrow. Next, let us apply the Fleming's right hand rule for arm CD. Arm CD, field, motion of the conductor inside, like this, field and inside, and this thumb indicates from top to bottom the flow of the current. And therefore, if the magnetic field is this way and conductor motion is inside, in that case the direction of the current is from C to D. So, the current flows from A to B and C to D. So, let us compute the circuit. Current flows from A to B, B to C, C to D, and D to, see here this line has come to R2, brush B2, current is flowing like this. Galvanometer, it indicates one side deflection, and then it goes, current goes like this, enters B1, slip ring 1, then like this, and from A to B once again. So, these arrows will indicate the direction of the current. These two arrows indicate the direction of the current in the coil, and these two indicate the direction of the current in the external circuit. From here to, from B1 to B2, this particular part is called external circuit of the generator, whereas from R1 to R2, this is called internal circuit and external circuit. So, externally, the direction of the current is from B2 to B1. Did you understand? Externally, the direction of the current is from B2 to B1 till this, till this rotates like this and comes. So, this is the next half cycle. That means ABCD has rotated like this and stood like this here. This is what it is. Now, so first half cycle is completed here. Second half cycle begins. In the second half cycle, once again, let us see here, magnetic field, the index finger this way, and direction of the arm CD, it is upwards once again, because this is how it is moving. This also, it has to come upward only. That is the thumb. That is how it is. Something like yeah, I think you should be able to. Just a moment. So, arm CD upward thumb, field is ulta, yes, correct now, and the direction of the current. Can you see now? Thumb is outward, index finger is north to south, and my finger, middle finger indicates from D to C current, and therefore current flows from D to C in this case. So CD comes upward because this is continuously rotating in clockwise direction, and AB goes downwards. CD comes upwards, and therefore current direction according to Fleming's right hand rule is this way, and in arm BA this is this way, current is in this direction. Therefore let us study the flow of current D to C, C to B, B to A, then R1 is connected to B1, and from B1 to galvanometer indicates the deflection in the opposite direction, then to B2 to slip ring 2 and DC. So this is how the direction of the current gets reversed in the external circuit. Check here, B2 to B1 in the first half cycle, in the second half cycle B1 to B2. This is how the direction of the current changes in one complete cycle, that is in 360 degrees of rotation of this armature coil. Beginning with this, the direction of the current changes 2 times, and therefore this is called an alternating current. What is an alternating current? If the direction of the current changes in one cycle, then it is called an alternating current. If the direction of the current in the external circuit remains same, it is called the direct current. I hope you have understood. You apply Fleming's right hand rule yourself, then you should be able to understand this. Okay, remember R1 is connected to B1 and R2 is connected to B2. R1 and R2 are called slip ring commutators, which reverses the direction of the current in the external circuit, and of course in the internal circuit also it is getting changed here. So this is the working of AC generator. Next, construction we have explained. Working, it works the same, whatever that I have explained is given over here, and alternating current is represented like this: current over here and this is a time over here. So the polarity of the current, this is a sine wave, and the polarity of the current becomes once plus, once minus, 1 plus, once minus. So from here to here, this is called one cycle, from here to here. Okay, so this is once plus, once minus. If the current changes here, the polarity of the current changes 2 times in one cycle. So if I say the frequency of the AC current is 50 Hertz, that means the direction of the current is changing 100 times in a cycle. 100 times 50 in 1 second. What is the frequency? 50 Hertz per second. Means 50 Hertz, 50 cycles per second. But in one cycle, current changes 2 times its direction. So 50 into 2, 100. 50 cycles into 2 times the change in the direction. 100 times the current changes in an AC circuit with the frequency of 50 Hertz. That you should remember. Okay, next. Same explained here. And what is the frequency of 50 Hertz? Meaning 50 Hertz means 50 cycles per second, or direction of the current changes 100 times per second, 2 times per cycle. AC changes direction after every 1/100th of a second. You can also say if 100 times per second the direction changes, so one direction change takes place in 1/100th of a second. So AC changes its direction every 1/100th of a second. That is also true. Okay. So before we start this DC generator, my suggestion would be you can note down from here. You can pause the video to note down this diagram also. Then the construction, working, and the cycle, how do you represent? Next half rotation, what happens, what is the meaning of frequency, etc. Okay, so I'll explain. I'll take a pause for 1 minute and then start once again the DC generator. This is a DC generator. Why this is DC generator? Check the direction of the current in the external circuit. In the beginning of the cycle, the direction of the current is from B2 to B1. in the next half cycle, check it. It is also from B2 to B1 only. So in the external circuit, the direction of the current is not changing. It is only in one direction, and hence it is called the direct current generator. Same thing, ABCD, what are the parts over here? ABCD, it is a rectangular coil. N and S are the permanent magnets. R1, R2 are called split rings. Those are split into two halves, and hence those are termed as split rings. And B1 and B2 are carbon brushes. G is the galvanometer. Now we have to move this into a field, isn't it? And therefore, let us move this ABCD coil in a clockwise direction. Meaning this arm comes towards you, or upward, I can say like this, because it's a 3-dimensional, it is upward, and the direction of the field is this way. Direction of the current, let us check once again in arm AB. Field, index finger, something like this, yeah, that is this way, north to south. Direction of motion of the conductor towards you of this arm. So the middle finger indicates the direction of the current, that is AB. So by applying Fleming's right hand rule, the direction of the induced current is from A to B, and in arm CD it is from C to D. So let us check the direction completely in the beginning of the cycle. As and when it is moved, these are the directions of the current: A to B, B to C, C to D, from D to R2, and R2 is connected to this coil permanently, and from R2, that is split ring R2, to B2, to that the galvanometer, and then to B1, R1, and then to A and B. So this is how it is completing. So once this comes to the half cycle, this is the status. Arm CD is here, arm AB here. Applying Fleming's right hand rule for arm CD, the direction of the induced current is from D to C. In arm BA, it is from B to A. Okay, but thing is, here R1 and R2 both have changed their positions because those are attached to the coil. So the direction of the current is now D to C, C to B, B to A, A to R1, R1 is connected to B2 here, and from B2 to galvanometer, once again to B1, R2, D and C. Is it right? Now check this R1, R2. Earlier R1 was in contact with B1 and R2 with B2. Now it is reversed because it has taken a rotation, and these coils are permanently attached to the split rings. So R1 is here, now R2 is here. R2 was on the right side, now R1 is on the right side. R1 is connected to B2. So as the coil rotates, R1, R2 rotate, but the slip rings remain same there as it is, and hence the direction of the current in the external circuit remains always same, that is from B2 to B1, and hence it is called a DC generator. I hope you have understood the working of this one. Next, construction, and this is how we represent it. Magnitude of the current is always same, either positive or negative, but it remains same over the time. So this is the representation. Working I have explained, half cycle, you can note down those things. Now finally, domestic electric circuits, this also will complete this. See, the domestic electric circuit looks like this. From the electrical pole, we take the connections to electricity board's fuse. Electricity board's fuse, this fuse, generally it is present on the pole, and hence it is also called the pole fuse. So it is the electricity board's fuse. It is not the property of us, but it is, this fuse is the property of the electricity board. So this is the fuse over here, and then there is a meter into our premises. From the meter, you can have a distribution board, which is also called main distribution board or MCB switch inside your house, and from this MCB, the connections will be taken to different rooms, and also heating circuits and lighting circuits. Heating circuits are the one in which heavy load is present, such as the geysers, refrigerators and toasters, all those will be connected, whereas lighting circuit are the simple ones which consumes about 5 amperes of current. whereas heating circuits will consume about 15 amperes of current. There are three lines indicated by three different colors. Earthing wire is indicated by a green color, live wire is indicated by a red color, and neutral wire is indicated by a black color. These are the standard conventions. We use the same, but already nowadays we have changed this already. The changed details are not there. So let us study only these things. So what is this earthing wire? Earthing wire, in our compound premises, we dig something like a deep, not a well it is, we dig the earth for about 2 meters, 1.5 to 2 meters, and put a big thick plate inside, and connect that with a copper strip, and cover that with salt, sand, etc., and that will be connected to the earthing wire. That earthing wire will be taken into our distribution box here, and then it can be distributed along with the other wires, but here it is shown directly, but we can definitely take it to right from the meter box to this, and then you can take it. So what is this function of earthing wire is, it provides the least resistive path, and therefore the earthing wire should be connected to the metallic body of the appliances such as the iron press or the washing machines, refrigerators, etc. Okay, so that even if there is a short circuit, or if there is a if the body of the appliance is conducting electricity, then that current will pass through the earth, because earth is maintained at zero potential, and a person who is operating or who touches the body of the appliance will not get shock, electrical shock, and thus the injury to the person is prevented. So earthing wire acts like a preventive measure. Okay, and live wire, which carries electric current, and neutral wire, which is used for completing the electric circuit. So pole, fuse, meter, main distribution box, and then it is taken to different rooms, and all these are in parallel combinations. So in parallel combination, even if one appliance fails, or if one room is not functioning, all other appliances should definitely able to work. And 220 volts is the potential difference between the live wire and the neutral. Neutral is maintained at zero potential, similar to the earthing wire, and therefore the potential difference between the live wire and the neutral is 220 volts. And these are the 3-pin plugs, 3-pin sockets, and in the 3-pin sockets, the top center hole is the one that is used for connecting the earthing wire. One will be the live wire and one will be the neutral wire. This is how the connection generally takes place. Okay, associated with this, there are some terminologies we'll rush through. What is earthing? The earth wire with green insulation is connected to a thick metal plate deep inside the earth near the house. This is used as a safety measure for the appliances that have metallic bodies such as electric press, toaster, refrigerator, etc. The metallic body of an appliance is connected to the earth wire. If there is a leakage of the current to the metallic body of the appliance, the current flows through the earth wire as it provides the least resistive path, and the user may not get a severe electric shock. So that is very important application. Next is short circuit. Whenever live wire comes directly in contact with the neutral wire, in that case the current in the circuit becomes very high, and whenever this unduly high current flows, we say the short circuit has taken place. When the live wire and the neutral wire come into direct contact due to damage in the insulation of the wires or fault in the appliance, current in the circuit abruptly increases, and this is called the short circuiting. So I hope you have understood. What is overloading? In one socket, such as here, in one socket if you connect lot of devices, then say for example 5 ampere is the capacity of the one switch. If you connect the appliances up to 10 ampere load, in that case we say that this switch or a socket is overloaded. So when the current in the wire is more than the capacity of the wire, it is called overloading. Overloading can occur when live and neutral wire come in contact with each other. Also overloading can occur due to sudden increase in the supply voltage. Also overloading can be caused by connecting too many appliances to a single socket. These are the different reasons by which overloading takes place. What is a fuse? First of all, fuse is a safety device which you should know. It is a safety device used for protecting the circuits and appliances due to short circuiting or overloading. So fuse wire is made up of an alloy of high resistivity and low melting point. This you have studied already in current electricity chapter. So generally it is made up of an alloy whose resistivity is high. So if there is a large current due to Joule's law of heating, heat will be generated and it will melt because of its slow melting point. So the two characteristics of the fuse wire are high resistivity and no melting point, and it should be alloy. Fuse works on the principle of Joule's law of heating. When the current in the circuit increases, the amount of heat generated is more and fuse wire melts. Thus it isolates the circuits and appliances completely and protects them. So this is the summary of the domestic electric circuits. Okay, so we have gone through a lot of things in this chapter. To summarize very quickly, first of all, before summarization, this chapter requires a huge amount of imagination and moreover the interest. It all depends upon the interest to learn the physics. I could have shown you by doing some small experiment, but so much of time is not available. We tried a little bit, but we couldn't do it properly. And I suggest some of these experiments you can watch in YouTubes and try to make yourself, like generator, electromagnetic induction, current carrying conductor displacement, all these things you can definitely do at home. Try to do those things. So what physics definitely requires a lot of imagination, and what we studied, very quickly to summarize, Oster's experiment. A current carrying conductor produces a magnetic field. Second, a current carrying conductor, whenever placed in a magnetic field, experiences a force, the direction of which can be given by Fleming's left hand rule, and that is the principle of DC motor. We studied how the DC motor works. And finally, electromagnetic induction. Whenever there is a change in magnetic flux associated with a coil, an EMF and hence the current is induced into the coil, and the direction of which is given by Fleming's right hand rule, and that is used to that is applied for the coil which is made to move, or the conductor which is made to move in a magnetic field. And finally, generators, which works on the principle of electromagnetic induction, and domestic electric circuits, fuse, earthing, overloading fuse, etc. These are the things. Now, in order to understand the second part, that is electromagnetic induction, and further, I have some video clippings. Please watch carefully. You will really enjoy that one. So let us switch back to the video clippings now. I think we'll take a pause for 1 minute. Here this video demonstrates about the electromagnetic induction by a coil.
Let us study electromagnetic induction with the help of a current carrying coil. We have taken two coils of copper wire with large number of turns wounded on a non-conducting roll. One of the coils with the largest number of turns is called the primary coil, which is connected to a power supply. And the other coil is only connected to a galvanometer called secondary coil. Insert the plug key and observe galvanometer for deflection. There is a momentary current in the secondary coil. We can see that the galvanometer deflects momentarily. Galvanometer needle jumps to one side and quickly returns to zero. Disconnect the plug key and observe. We can see that the needle of galvanometer deflected again momentarily, but to the opposite side. As we change the supply voltage, there is a momentary deflection in the second coil. We have observed that a potential difference is induced in the secondary coil whenever the electric current through the primary coil is changing. So, we can conclude that the process by which a changing magnetic field in a conductor induces the current in another conductor is called electromagnetic induction.
Here we will see practically the video lecture that demonstrates practically the induction of the current and the EMF.
Hi and welcome to High School Physics Explained, and today I want to demonstrate Faraday's law and give you a bit of an explanation as well. So in front of me I have a coil, and that is connected to this ammeter or galvanometer. And I also have a rare earth magnet, and this magnet is facing so that the north is facing outward like so. What's going to happen when I insert this magnet into this coil? You see the needle deflect. What if I do this faster? You should see that the needle deflects a greater amount. So what's going on? Well, Faraday's law in essence says that the rate of change of flux causes the production of an EMF, or in other words, what is commonly referred as an electromotive force, though in reality it's talking about a voltage. So when I place the magnet in, the magnet has a magnetic field around it. Magnetic field lines are radiating out from the magnet. And as I insert the magnet into the coil experiences a change in flux. That is, these magnetic field lines are crossing over the wires. And the rate at which that occurs is causing a production of an EMF. Now, EMF is like a voltage. So, since I'm producing a voltage and we now have a closed circuit, I'm also producing a current as a result. And so we see that in the deflection. Now, the direction of the magnet, or the direction of the relative motion between the magnetic field lines and the wires, determines the direction of the EMF and hence the current. So if I pull it out, you're going to see it deflect the other way. Now, what will happen if I turn my magnet over so that the south is now facing outward? We're going to see the same effect with one small exception. That is, the deflection will be in the opposite direction. Why? Again, because the magnetic field lines are now in the opposite direction. Now, what happens if I hold it stationary? You'll see no deflection whatsoever. That's because we don't have any changing flux. We don't have any rapidly changing magnetic field lines crossing my wire, and so I have no EMF. So that's a very simple demonstration of Faraday's law. But let's say I don't want to use a magnet to generate a rapidly changing flux. What can I do then? And now in a variation of Faraday's law demonstration, you'll see I still have my solenoid over on this side connected to the ammeter, and there's no connection to a power supply. On this side, I have an ammeter, a solenoid, and a rheostat, which allows me to control the amount of current. So if I turn it on, I'm going to get a deflection. As you would expect, a current is flowing through the solenoid. And of course, it will turn to zero when I turn it off. Now, what happens if I place this on top of the solenoid like so? There's no connection to the bottom solenoid. Let's see now what happens when I switch it on. You may have noticed that a very slight deflection takes place, but the deflection lasts only momentarily. Now I'm going to accentuate the deflection. Now this is just some metal rods, and I'm going to place them in the center of the core. Now these are not causing these two solenoids to be connected electrically. In other words, there is still a separation of two different circuits. The only thing I've done is I've inserted some metal core, which is going to concentrate my magnetic field lines, and I'm going to demonstrate this when I turn it on. Again, watch what happens to the meter over here. Now when I switch it off, what do you notice? Well, the first thing is that the direction of the deflection is opposite to the direction of the current. So the current that is going to go from this circuit is clearly going in the positive direction, but the deflection here occurs in the negative direction. When I switch that off, you're going to see that the deflection heads in the positive direction. The other thing you might notice is that the deflection only lasts momentarily. It lasts for about the time that I'm switching it on, but returns quickly to zero. Similarly, when I turn it off, it deflects and returns back to zero. Again, Let's explain what's going on. If I just pull this out of the road, when I turn this on, we start with a situation where we have no magnetic field lines. But when I turn the current on, we are having a developing magnetic field, a growing magnetic field. If I place my coil in the midst of the growing magnetic field that this bottom solenoid is generating, this top coil is experiencing a rapidly changing flux, and the rate of which, of course, is determining the EMF that is generated, and following on from that, the current that we get. But when I leave the power on, the current is steady, which means my magnetic field, which is still there, is not changing. It's staying steady, which means the top coil is not experiencing any changing flux. What if I turn it off? Well, I suddenly go from a very large magnetic field that this top coil is in, that is going to rapidly decrease to a point of zero because of the current, of course, switches off. Again, it's not an instantaneously disappearing magnetic field. It drops away, which means the top coil is now experiencing a rapidly changing flux in the opposite direction. Hence, the needle will deflect in the opposite direction. So turning on and off rapidly will give me an alternating current. I have a video on the induction coil, which in essence works on the same principle. Switching it on and off rapidly will cause me to have an induction, that is an alternating supply in the top coil. The last thing I want to mention is the concept of Lenz's law. And Lenz's law is such that whatever generates the magnetic field, an EMF is generated so that it opposes the change. So if I were to lift this up like so, and I were to turn this on, this would generate a magnetic field. If the current was going in the direction of that, I'm going to get a current that causes the top section here to be a north pole. This one will generate an EMF, but the result is that the current that's generated will produce a pole in the opposite side. It negates it. So in other words, we're going to get a north pole generated at this point as a result of the north pole being generated at this point, which is the reason why the current is going in the opposite direction when I switch it on. Similarly speaking, if I switch it off, that's a very important principle, Lenz's law, because it actually is a follow-on from the law of conservation of energy. Now, I have a video that discusses Lenz's law in greater detail, and I encourage you to watch that. But both demonstrations that I've now shown you is a demonstration of Faraday's law. That is, the rapid change of flux with respect to time will cause an EMF, and the negative sign in the formula of Faraday's law signifies Lenz's law.
Now in this video clipping, we'll see the working of AC generator.
About an AC generator. An AC generator is an electric generator that converts mechanical energy to electrical energy in the form of an alternating EMF or alternating current. Working principle of an AC generator. An AC generator works on the principle of electromagnetic induction. In electromagnetic induction, when there is a relative motion between a coil and a magnetic field, an electric current or EMF is induced in the coil. Parts of an AC generator. An AC generator has an armature ABCD. It is a rectangular coil with many turns wound around a soft iron core. A shaft. It can be rotated rapidly. A field magnet. It may be a strong permanent magnet with concave poles. Two slip rings S1 and S2. These are connected to the armature and thus rotate with it. Two brushes B1 and B2. They provide electrical contact with the slip rings and a load which may be a galvanometer as shown. Working of an AC generator. When the armature rotates between the poles of the field magnet, the magnetic flux linked with the armature changes continuously. As a result, an EMF is induced in the armature. This in turn produces an electric current through the armature and the galvanometer and through the slip rings and the brushes. Note that the galvanometer needle swings between the negative and positive values. This means that an alternating current is flowing through the galvanometer. Direction of induced current. Initially, the armature ABCD is vertical with its arm AB up and CD down. The direction of magnetic field is from left to right. As the armature undergoes a half rotation clockwise, arm AB moves down while arm CD moves up. According to Fleming's right-hand rule, the current will flow in the direction DCBA. So, the current will flow from B1 to B2 through the galvanometer. Now during the next half rotation, arm AB moves up while arm CD moves down. Again by Fleming's right-hand rule, current will flow in the direction ABCD, that is, from B2 to B1 through the galvanometer. Thus, the induced current changes its direction every half rotation. Graphical representation of induced EMF. Suppose the armature takes t seconds to complete one rotation clockwise. At time t is equal to 0 second, the armature ABCD is vertical with arm AB up and arm CD down. At this position, when the armature rotates, the rate of change of magnetic flux is momentarily zero. Hence, the induced EMF at this position is zero. During the first quarter rotation, the induced EMF increases. Then, at time t upon 4 seconds, the armature becomes horizontal. At this position, the rate of change of magnetic flux momentarily attains the maximum value. Therefore, the induced EMF at this position is maximum. During the second quarter rotation, the induced EMF decreases. Then, at time t upon 2, the armature again becomes vertical and therefore the induced EMF is zero. During the third quarter rotation, the induced EMF increases but has an opposite polarity as compared to that of the first half rotation. At time 3t upon 4 seconds, the induced EMF attains its maximum negative value. During the fourth quarter rotation, the induced EMF decreases and becomes zero momentarily at time t seconds, as the armature is vertical once again. So the magnitude of the induced EMF is sinusoidal. In this module you have learned an AC generator is an electric generator that converts mechanical energy into electrical energy in the form of alternating EMF or alternating current. An AC generator is based on the principle of electromagnetic induction. An AC generator consists of an armature, a shaft, a field magnet, slip rings and brushes. The graph between the time and EMF generated by an AC generator is sinusoidal.
Here we'll study the working of a DC generator, that is direct current generator.
Hi and welcome back to my YouTube channel. Have you ever wondered how DC generator works? And what are the basic parts of a DC generator? This video will give you the answers to these questions. We will start with the basic parts of the elementary DC generator. As you can see, the configuration of DC generator is pretty simple. The stator is a fixed part of the DC generator. The stator consists of permanent magnets, 2 of them north and south poles, which is placed to fit around the rotor. The main function of the stator is to provide the magnetic fields through which the rotor or armature coil is rotated. Armature loop are generally placed in slots of armature core. The armature coil is formed by connecting several loops in the series. Armature winding is formed by connecting several coils in series. The armature loop cuts the magnetic field, due to which an electromotive force, EMF, is induced in it. The split ring is a movable device used for reversing the polarity of the current. It's made of copper. The ring is divided through the middle into 2 parts. We must use the split ring to achieve single direction of current. The brushes are made of carbon. These are rectangular block-shaped. The only function of these carbon brushes of DC generator is to collect current from commutator segments. A galvanometer is an analog electromechanical actuator that produces a rotary deflection of some type of pointer in response to electric current. So how does the DC generator work? Firstly, we don't want that current direction to change. We want it to remain the same at all times. Let's say in this direction. So, how do we do that? Now, to make sure that the current direction remains the same, what we require is that these brushes constantly keep changing contacts between these wires for each half of rotation. So, if the current flows in this way, in this position, this brush must be connected to this wire. So current flows like this and comes out. But when the coil rotates, you can see that when the coil comes to this position, the direction of the current changes. If we want to keep the current in the same direction, we must this brush to be in contact with this wire. Right. And then again, when the coil comes to this position, again the direction of the current changes, and again we want this brush to come in contact with this wire. Probably we already learned that. For every half rotation we must change contacts between brushes and wires. But how do we make this process happen automatically? We can automate this process by adding split rings. Split rings, as the name suggests, is a ring that is split in between, giving 2 half rings with the same gap in between. Now let's see how the split rings automatically change contact for every half a rotation. So right now this brush is in contact with this half part of the split ring, violet color. When the coil rotates and comes to this position, the direction of the current changes, and this brush now is in contact with the other half part of the split ring, pink color. This arrangement provides that current flows in the same direction. Again, as the coil comes to this position, finishing another half a rotation. You can see that this has only changed contact. Brush is in contact again with the violet color, half part of split ring. In this way, the DC generator is built, where the current only flows in one direction through any external circuit, and in this arrangement, with brushes and split rings, which helps us to automatically change contacts, we call them commutators. So split rings act like commutators. The next thing we must mention, that it's really important for working principle of DC generator, is how can we determine the direction of the current, magnetic field and force. To determine all this, we must use Fleming's right-hand rule. So we will explain how can we use Fleming's right-hand rule. As you can see, the rotation of the coil is clockwise, and the force acting on part of the coil AB pushing that part of the coil upwards. So to know the direction of the induced current, we apply the Fleming's right-hand rule. How do we do that? We place our right hand so that the thumb points up, showing the direction of the force. The index finger or the finger pointing in direction of the magnetic field from north to south pole, and middle finger will point in the direction of the induced current, which is in our case from A to B. Similarly, to find the induced current in a part of the coil CD, we again use Fleming's right-hand rule. So the rotation of the coil is clockwise, and the force acting on part of the coil CD pushing that part of the coil downwards. The thumb points down, indicating the direction of the force, indexed finger or for the finger pointing in direction of the magnetic field from north to south, and the middle finger will point in the direction of the induced current, which is in this case from C to D. So to conclude, the induced current follows the path ABCD of the coil. The effect of the split ring commutator in DC generators is to ensure that the induced EMF is always in one direction. We can see that in this graph, where V represents the amount of induced EMF and T represents time. You will notice in the graph how the sine wave changes with rotational speed of the coil. The coil in this case has clockwise rotation. Increased rotational speed of the coil increases the amount of induced EMF. The induced EMF has a positive sign. Also, you see the example how the sine wave changes with rotational speed of the coil, when the coil is rotating counterclockwise. Again, the increased rotational speed of the coil increases the amount of induced EMF. In this case, the induced EMF has a negative sign.
Yes, students, I think the video clippings could give you in detail about the three-dimensional models and three-dimensional aspects of all those concepts that we have discussed so far. So I have completed this magnetic effects of electric current in all respects. This chapter is complete. In my next lecture, I will be taking the question answers, exercise questions, in-text questions, and few selected exemplar questions also. So let us end the lecture. See the next in the next class, in the next lecture, and thank you for watching.